Thank you for the introduction. Welcome everyone, and thank you for the high attendance. So my name is Timar, and the title of my tutorial is From Passive to Active, Exploring the Benefits of Active Learning in Data Science. So my name is Timar again. I'm from Hungary originally, but I've been living in London in the last 3.5 years. I work as a senior data scientist at Mazen, which is a Saudi fintech startup. I pasted their mission statement on the slide, and I can tell you that this is very accurate. A few things about my professional expertise and interests. So I'm a Bayesian. I love Bayesian inference when I can apply it. I enjoy working on experimentation problems like A/B testing and causal inference and that sort of stuff. Lately, I've been training a lot of language models and working on NLP, but I have experience in computer vision and video analytics too. So, what are we going to do today? So, this was supposed to be a tutorial and like a hands-on tutorial, but I tested the hands-on part and it was too long. So there's not going to be any hands-on coding right now. The talk will be like 10 minutes shorter because of this, and you gain some time before lunch. And we're going to talk about active learning. And first, I will give you some motivation as to why you want to learn active learning, and then we'll talk about the active learning process. And then we'll have a short literature overview, and then we will define what makes a data point or a data sample informative. And then we'll introduce a couple of concepts that are useful for active learning. And then we'll generalize active learning so that it works with batches of data. And then we'll talk about like common metrics and distance measures with which you can compare data samples. And then I'll just quickly go through the hands-on part. In a Jupyter notebook, I will implement a simple active learning system, and then, yeah, some closing thoughts, and I'll have some time for questions. So the first angle from which I want to motivate active learning is scaling. And what I want to say about that is, like, there's this observation in machine learning that if you start out from a small model with a limited amount of data and like a limited compute budget, and if you start scaling these up simultaneously in tandem, so you basically replace your smaller model with a bigger model and a bit more data, and you spend some extra money on that, and you scale it up even further, all of these, then there are these scaling laws. I basically pasted a result on this figure from a key result from a paper where they studied scaling laws of transformer networks, and their observation was that, like, you can see that on the horizontal axis you have these three parameters, like your compute size, your dataset size, and your parameters, and the horizontal axes have a log scale, each of them. And you can see that for several orders of magnitude, there are these fancy scaling laws, and it is even true that for the high end, so for the high accuracy limit, there seems to be no limit yet. So the scaling laws hold in the higher limit, and of course. It's also an observation that if you fix even one of these parameters, then, like, for example, you fix your data set size. You don't have any more data that you can add to your system, but let's suppose you still keep increasing your number of parameters and your compute, then the observation is that you'll have diminishing returns, and if you fix just one of these parameters, it will become a bottleneck. And it's fine, but unfortunately we know that compute is bounded, so you cannot really just scale until infinity. So we need to do something in order to break out of these scaling laws to improve model training and make inference and training more efficient. And there are several ways of doing that. The first point that I want to mention isn't really a natural continuation of my argument, but if you just understand the scaling laws, you can shorten your development time by just pinpointing the right hyperparameters with which you want to train a neural network. But the rest of these points are actually like improvements and make model training and inference more efficient. And one method that you can try is model pruning, where it's important to make a distinction between like structured and unstructured model pruning, where unstructured model pruning means that you have a model, you have some weights, and by some kind of logic, you say that, okay, for example, if my weights are very close to zero, I will start switching them off and canceling them out completely. And then there are some research papers that, like, of course, it depends on the domain, but you can switch off like 50% or 70% or 90% of your weights without losing your test accuracy. But unfortunately, like, unstructured pruning means that you don't really change the structure of your neural network, and thus it isn't really faster. Your GPU won't do computations faster. So a better way of doing model pruning is structure model pruning, when you actually change the structure of your model, but still want to retain or improve your test accuracy. And another way to improve model training and inference efficiency is by algorithmic innovation. So we know that some activations were better than others. We know that regularization is really helpful. And we know that for a wide range of problems, like model architectures are just better than others. So for example, we know that on the state of the art for a lot of tasks seem to be transformers, and they seem to be outperforming LSTMs. And of course, you can use technological innovation as well. So for example, you can use OpenAI's Triton, which is like, so if you have a neural network, Triton can look at it and you can say that, oh, you have 3 layers in your neural network, one after another, and what about like compiling just one GPU kernel for these 3 layers? And then it will just compile one kernel for you and everything will be faster. It's like a software, it's acceleration technique, or you can use better hardware. And one like relatively hip way of improving your model training and inference is data pruning. So usually you don't want to ruin your precious batches during neural network training with uninformative data points. So data pruning is a technique in which you, in just one shot, want to filter your data and select the most informative samples and only train with what's necessary, and don't waste time with the rest of the easy samples. And if you learn about active learning, you'll immediately get better at data pruning, because in my mind they are like siblings. And the other angle from which I want to motivate active learning is transfer. And here I just want to recite a key result from another paper. And here the authors, so they trained transformer networks, and the goal of the transformer networks was to predict Python code, like they wanted to do next word prediction on a Python code. And they had 2 training curricula, so they had 2 structurally identical transformer models. The first transformer models was pre-trained using natural language and then fine-tuned on Python code, and it's shown with blue on the right-hand side. And they had another transformer model that was pre-trained from scratch on Python. And on the right-hand side, the horizontal axis is the number of Python characters in the data set. Again, it has a log scale, and your vertical axis is, so it's basically an extra prediction cross-validation test loss. And the observation is that if you fine-tune a transformer model with Python data that was pre-trained on natural language, it needs much fewer samples. So in other words, if we reverse this, if you pre-train from the get-go on Python, you need a lot more Python characters to match the accuracy of a transformer that was first pre-trained on natural language. And basically, you can see these, df is the size of a fine-tuning data set, and dt is the number of characters that are needed in order for the orange model to match the accuracy of the blue model. And the authors showed that for some test losses, the number of characters in the fine-tuning data set are like much fewer. There's a multiplier, like you need 1000x more data points or Python characters for the pre-training. So it is really exciting because when you just think about transformers and you see that, oh my God, they have like 50 million and 100 million or 250 million parameters, or even more, of course, because these are considered small now. Surely, like some transformer models, like read the internet multiple times, and they consume more data than any human. And like, if I'm sitting on a pile of huge annotated data set, let's suppose you work at a bank, or like your company has a website that has high traffic or something like that, and you have a lot of unannotated data, your intuition can be that, oh my God, like I need a lot of annotation in order to exploit that data and use that. But with transfer learning, we can see that this is not the case. And you can still try to annotate some data, and with fine-tuning, you can get state-of-the-art results. And like, okay, then what should you do? Well, the first idea is to like start out from your unannotated pool of data, and then there's a paradigm called passive learning that like you should just deduplicate it and perhaps like get a random sample from the most recent part, and then you end up with a data sample, and then you can hire some annotators, some experts who can annotate it for you. But unfortunately, if you do this, you risk asking your annotators to label very similar data points, and their work might be repetitive, and in some cases you might ask them to annotate outliers or annotate points that are too easy and not really challenging for a model. So the next idea is to use data pruning. So we talked about this. So in one shot, you can just, by some kind of logic, you can try to filter your data point and retain retain a certain percentage of it that is the most important part. And active learning is an improvement over this. And the idea is that if you have a model, if you want to measure the informativeness of your unannotated samples, you can ask your model. So, of course, you can compare your data points themselves, but if you have a model, maybe it can tell you how certain or uncertain it is about certain data samples. And then the process of active learning goes as follows. So you start out from an annotated pool of data, and then you have an active learning service, and the responsibility of the active learning service is to choose a couple of points for annotations. And then once you have an annotation data set, you can pass that to forward that to an annotation tool where your experts pick them up and they annotate it, and then they create this annotated data set for you where the narrow column represents that now the experts gave you a target column. And then if you have input-output pairs, of course you can train models, and you can push them to a model registry, and here the cycle goes back into itself, because in the active learning service you can then ask your model as to which are the data points that should be annotated next. And the expectation from all this process is that as time goes on and as you create newer and newer active learning batches of data, you want your test accuracy to just shoot up. and be as efficient as you can. And here I want to show you a couple of important methods from the literature. So, like, of course, we talked about informativeness. So you want to select points that will be like informative for the model. And one idea is that you start out from your unlabeled pool of data, and then you train a model, and your model usually has a target column, and you have ground truth samples and prediction samples, or predicted predictions. And one idea is to add a little sidekick to your model that tries to learn your loss. And then it's like inception a bit, because then you have a loss of your loss, but yeah, you don't use that. But anyways, the idea then is to predict your loss on the unannotated pool of data and use the samples from the unannotated data that have a big loss. And I hope that as we go through with this talk, this tutorial, you will understand the pros and cons of these approaches. And one other important method that I want to mention is a Bayesian technique. So, of course, if you use Bayesian inference, mathematically it will be very elegant, and you can define a lot of things very clearly. So here in this paper, the author said that, okay, the objective of active learning is that you start out from a certain data set, and you have a model, which is basically, you can define it as a joint probability of the data and the target column and your model weights. And the question is, which data to gather next? And they have two approaches. The first approach is to select the next data point that maximizes the informativeness of the weights, which means that, like, I want to select a data point that, if annotated, our expectation is that it will like shrink the probability distributions of the weights. You'll be much more certain about the weights after the annotation. And of course, you can similarly try to maximize the informativeness of your target random variable. And they have two choices of information measure. So you can use your change in entropy. So the concept is that before annotation, you have a probability distribution over your weights, and you can compute the entropy of that, which will tell you how, like, it will be something like the width of your distributions. And then you can compute your entropy after annotation, and if your weight distributions got narrower, then yeah, that's a good point to annotate. And of course, you can do something similar. You can use the cross entropy between these two distributions. And there's another Bayesian result. So there's this paper, they use Bayesian neural nets, but this idea applies as well for probabilistic models like conditional random fields. And the idea is that if you compute the mutual information between your target variable and your weights, then, like, if the mutual information between these is high, it means that if you learn information about one of them, probably you learn a lot of information about the others. So, and it's called Bayesian active learning by disagreement, because you can see the mutual information formula, and on the left-hand side there's the entropy of the target variable, and on the right-hand side, so it's basically an expectation value over the models that you sample from the Bayesian distribution. So, like in Bayesian neural nets, you sample a lot of neural nets. And in order for the mutual information to be high, the left-hand side needs to be big and the right-hand side needs to be small. And the right-hand side is only small if for the sampled models, your entropy is always small. So in other words, these both can only be true if the models that you sample from your Bayesian neural net are usually very certain about your target column, but they disagree. And that's why it's called Bayesian active learning by disagreement. And in the first paper, they sum this up for multiple samples to do batching, and that's not a good idea because mutual information doesn't really sum up. So in the subsequent paper, they did joint scoring, which is easier said than done. So they had an approximation, but yeah, this is the idea. But usually we don't work with Bayesian neural nets, so it's unfortunately rare for a couple of reasons. So there are a couple of results for non-Bayesian models, and there are two ideas: expected model change and expected error reduction. And the idea is that if you start out from a pool of unlabeled samples, and let's say that you have a multi-output classification model or the scenario, and then you can process all of your unlabeled samples through your model, and basically your model, of course, usually your targets are these one-hand encoded vectors, and your model's output are these probability distributions. We'll talk about whether these are probability distributions, but basically it's a vector that sums up to 1 and it's positive. And okay, you have these probability distribution looking things, and then of course you don't know the true label of your unannotated sample. But you can still assume that a certain sample comes from the 0th output class. And then you can assume that that sample comes from the first output class, etc. And for each of these cases, you can get the gradient of your last layer, let's suppose. What would be your gradient if the target column, or sorry, the true class of this specific sample was 0 or 1 or etc. And then you can basically compute a weighted sum over your probabilities and your gradients. And the idea is that if your gradients are big, that means that your model is needs to work a lot in order to learn that. Your model is extremely surprised. And but you can do the same idea with losses instead of gradients. Now from the literature overview, I want to go through a heuristic, opinionated implementation of active learning. And first, I want to define the objective of it. So, of course, we want to find the most informative samples in an annotated pool. That was that is our objective. But let's say you define informativeness by my model uncertainty. And let's say that, again, we have a multi-output classification scenario where you pass your samples to your model, and then from each of your samples, you compute a probability distribution. And in the where's my laser pointer? And in this second and in this third case, you can say that, oh, the model is pretty sure that the output is this, and this is the true output class, and your model is pretty sure that this is your output class, and in the bottom in the front. So about these, your model is not really sure. It is confused as to what the true sample is, or true output class is, and you can try to somehow quantify this uncertainty or this confidence. And there are multiple ways. You can see at this figure on the bottom right corner. So you can quantify uncertainty as your least confident prediction. So basically 1 minus the minimum of this probability distribution or probability mass vector. Or you can compute it as the difference of the highest value in this array minus the second highest value. Or you can compute your Shannon entropy. And of course, these are triangular simplexes where so this example is a 3 output class problem where the corners of the simplexes represent points represent the cases where the model is sure about a certain outcome, and the center of the simplexes represent a case where the model is completely uncertain about the outcome. And you can see that like these heat maps, these uncertainty heat maps are completely different. And for example, we can see that Shannon entropy penalizes complete uncertainty much more than just uncertainty between two output classes. So yeah, be careful when you're choosing them. And okay, like let's say we have a good metric to measure uncertainty, and then we associate it with informativeness. Well, we're still not there yet. So if your idea is that, okay, like I have my unlabeled samples, and for each of my samples I can compute the model's uncertainty, and then I can sort this, and I can pick the top 50 items from this table, it's not necessarily a good idea, because then you risk like multiple things. For example, usually your model is really uncertain about outliers, so and you don't generally want to annotate outliers, and like knowing the uncertainty about a certain sample doesn't mean that you like there can be multiple samples that look completely the same and have the same uncertainty. So you might be sending the same sample to your annotator. So we feel that you want to select a batch of points where each of the points are like diverse and representative. So like your batch needs to be diverse, and each of the points must represent multiple points. So if I send in one point to my annotators, I want to be sure that that point represents like 5 or 10 other samples, and my model can learn those too. And we feel that like these are geometric concepts, and we will need like some kind of metric to work with this geometry. And just one note about whether like the output in a multi-output classification of a neural network is whether it is a probability or not. So there's this textbook case where like if you have a model that has to classify whether a certain image is a fork or a spoon. Of course, these are textbook outputs, but for example, if you feed a spork to your neural network, it will say that like most probably the probabilities of both output classes are the same, and your model is right. I mean, this is like your model is extremely confident, and your model is right. And you can even feed some noise into your neural network, and you'll get some garbage out. And in this case, most probably your model is extremely uncertain and not confident at all. So like, it's important to note that these probabilities don't really tell you the confidence of the model, and you need to work on this. So the most we can say is that like these probabilities give us our models ambiguity and not uncertainty. And the textbook solution to mitigate this problem is to use Bayesian neural networks. But of course, like unfortunately, then you need to do sampling, and which is slow, and it's more complex. So you have more hyperparameters. You need to choose priors, and etc. etc. So one way to kind of mimic Bayesian neural networks is to use dropout. So if you have dropout, you can act like you have model ensembles. But yeah, you can just use model ensembles. So you can try to use multiple models, and yeah, consult the evidential deep learning literature in order to learn more about this. And back to active learning. So I would like to give you the visual intuition as to what type of samples that we want to pick for annotation. So let's say that on the left-hand side, you have basically, these are your samples, and the purple circles represent unannotated samples. These green circles represent fixed samples, which means that they have already been annotated, and these orange ones are the ones that we mark for annotation right now. And For example, you can choose a batch like this, in the middle figure. And here, most probably, so your active learning process chose this point, which is most probably an outlier. It's out there by himself, alone, and most probably, if you annotate that, you don't know much about your data. And your active learning process also chose these 2 points, which are very, very close to, first of all, each other and another fixed point that has already been annotated. So, annotating these doesn't really give you more information about your domain. So, a much better choice of active learning selection is this, where most probably your active learning service correctly recognized that this cluster wasn't annotated at all. Your active learning service recognized that it is not going to touch this one, and it's very frequent that usually you have these long clusters in your feature space, and you're better off choosing points from the other ends of your long clusters than just than points closer to your already annotated points. And I want to introduce 2 concepts in order to define geometry, and we feel that we have to kind of define something like a point density in feature space. And one way of defining a point density or sample density in feature space is by using a nearest neighbor search. So let's suppose that let's define a concept or a quantity called diversity in a way that so you say that the diversity of your unannotated samples is their average distance from their n nearest marked or annotated samples, and it looks like this. So this is your unannotated sample, and these are the 5 nearest annotated or fixed or marked samples from it. And of course you want to maximize this distance. So so you have these 5 nearest neighbors, and you can average these distances, and you want to maximize this. You want to be as far from these points as possible. And then similarly, you can define something called isolation, where basically you do the nearest neighbor search in the purple part of the graph, in the unannotated part of the graph. And basically, when your nearest neighbor, when your average distance from your nearest neighbors is high, that means that you're far off in the distance. And basically, you want to minimize isolation. So that minimizing isolation will give you representativeness. And so it's important that basically nearest neighbor search is not for free. So if even one subgraph here, the purple or the rest of the graph is too big, your nearest neighbor search will be very, very expensive. So one possible idea is that usually you're sitting on a lot of data. And of course, you don't want to do this with all the data that you have. So usually you can try to subsample your unannotated data pool to a size that will still be very informative, but tractable at the same time. And then we can refine this active learning service. And we can say that, okay, so we have an unannotated pool of data, and then just by looking at our data, we can construct this nearest neighbor graph, we can compute divergences, and we can compute isolations. And of course, we have a model, and completely parallel to the nearest neighbor graph, they are completely independent, we can compute prediction uncertainties or informativeness measures. And then if we combine divergence, isolation, and uncertainty, we can compute active learning scores in some kind of way. And then we can use these active learning scores to select the next batch to annotate. And computing densities is tricky. So the real complexity comes from the fact that isolation and diversity are computed on different parts of a graph, and if you mark one sample to be annotated, it suddenly jumps into the other, from the unannotated part of the graph to the fixed part of the graph. So it's tricky, but in theory, how you should do this active learning optimization is, so you should first start out, so let's say that you can parameterize a selection using Boolean variables, where these m's mean that mj equals 1 means that your jth sample is marked for annotation. And then if you can define a diversity function and an isolation function that that work on these Boolean representations, and then of course you can do some kind of optimization. But this is tricky, and one idea is to so if you want to base your isolation and your diversity on your 4 nearest neighbors, you can try to do a nearest neighbor search with like 8 or 12 neighbors. And then you end up with, like for each node in your unannotated pool, you end up with a list of the closest samples from you, and the list of the closest samples from the fixed and marked subpart or subgraph. And then you can use these bigger lists, and it's okay if one item jumps from here to here. You can still handle that. And then you can approximate an active learning function where, yeah, basically you sum up these like divergences and isolations, and yeah, the uncertainties should also be here. But the point is that then you can do some kind of linear optimization. But this is very complex. Usually people don't want to implement this, and in the literature there is no one really mentions this. People use this method. So what people do is they kind of apply active learning sample by sample, and basically they start out from a feature space, and then they do active learning for just one sample, and they choose that sample, for example, and then that sample becomes fixed. And the active learning service chooses another sample, and it's basically a one-by-one process. And yeah, unfortunately, you have to do a nearest neighbor search in every step, or somehow you need to update your representation internally about the graph. And one other idea is that, okay, instead of one by one choices, you can randomly choose a batch. Like you can get like, yeah, basically you can randomize this batch, and it doesn't even have to be completely random. You can weight by uncertainty, or you can try advanced ideas, but at the end you need to you need to aggregate the active learning scores and choose the best configuration, and you can pass that to the next like to your annotators. And of course, you want to be able to debug these concepts. So this is a tricky algorithm to implement. So my suggestion is that is to try to visualize these manifolds. So usually, what happens is that like you first embed your unannotated samples. So for example, your samples are like, they are text. And then you use some kind of vectorization to featureize your text. And so basically you embed your text in a high dimensional space. And you do all this diversity and isolation maneuvers in that high dimensional space. But if you want to debug that, you can use these algorithms to basically map your manifolds into 2D or 3D, and unfortunately there will always be distortions. So like mapping a high-dimensional space into a two-dimensional space isn't going to be perfect, and some points that are close originally will be far away in this mapped space. But yeah, still it's a really great way to debug active learning. And sorry for the label size. Yeah, it's a bit blurry, but basically, yeah, this is one manifold visualization. This is an isomet visualization of a document labeling data or test set or training set, where your output classes are like topics of the document, and yeah, this is what it looks like, and you can try to visualize your divergences and nearest neighbors and everything here. And okay, so I touched upon this very briefly, but of course you need to encode your features somehow. So like in order to like define this geometry, so you basically need metrics. So you need to be you need to be able to compute distances between samples. And one idea is that, okay, you first encode your sample in some way, and then there are a lot of distances here. So just consult the sklearn metrics pairwise module. And of course, these are implemented elsewhere as well in TensorFlow and etc. So you can see cosine similarities there, and all kinds of distances. And the tricky part is encoding your features into a high-dimensional space. And for example, if you have some text, one of the simplest solutions, or like a solution that you can see in most of the tutorials is to use DFIDF, which is like an advanced count vectorization, where you like use the counts to encode some kind of meaning. And you can, like, a bit better, or well, I should say much better approach is to like use word embeddings and somehow like aggregate the word embeddings of your documents. And an even better approach is to, like, if you're working with natural language, and then you can just take a transformer model off the shelf that was trained on the natural language, or basically your domain, and then the output of a transformer body will be meaningful for you. Like the contextual representation vector that the transformer body returns will be just a very good encoding for you. Or you can basically put a classifier head on a transformer, and you can use a hidden layer of it, or like some kind of activations. And there are similar ideas in computer vision, so you can use an internal representation of an autoencoder. You can use these Siamese networks, like for these networks for intrusion detection, which output these re-identification representations of faces, for example. You can use that, and there are other ways to featureize your samples. For example, there is this funky thing called random forest proximity, where the idea is that first you try to train a random forest on your samples, and of course a random forest is a set of trees, and two samples are then considered similar if they share the same exit nodes on these trees with another sample. So if one sample trickles down the forest the same way as another sample, most probably they are very, very similar. And yeah, there are a lot of ways to do this. A couple of things that I need to mention about metrics is, like, first of all, like, we're in the midst of an AI revolution, and now there's like a vector database, like new vector database almost every month. And you can work really well. There are a lot of libraries that handle dense vectors. Sparse vectors are slightly harder to handle. So if you have sparse vectors, for example, TF-IDF returns sparse vectors, then, for example, computing cosine similarities is a sparse matrix multiplication. And like, of course, you can use activations, and you can use metrics that somehow come from a model, but there are a few issues with this. So, for example, if your model is not really advanced yet, it didn't really have time to capture a certain domain well, then most probably an internal representation of the model won't be too advanced. And basically then, if your model cannot capture your samples, in some cases, your model can then put a lot of samples into just one big cluster in the feature space, and then you won't be able to really use isolation and divergence. So it's problematic, and of course, like these internal representations, these activations weren't even designed to behave well as metrics. So they were designed to be picked up by the rest of the neural network and do something meaningful, but not to be like basis of cosine similarity. So you have to be really careful. And data pruning is pretty big now. And so it's very, very similar to active learning, but usually in data pruning, people already have a target column. And of course, the whole point of active learning is that you don't. But if you have a proxy for a target column, you can go through the data pruning literature. It's really good. For example, there's a really good review here. I hope you can see it. For example, there are these forgetting scores where the concept is that, like, if you train a neural network, you can check whether certain samples are like easily learned and then like learned forever by the model, and whether other samples are constantly forgotten by your model. And if your model throughout its training process constantly forgets some samples, that's a good indication that like most probably that's an informative sample, or at least challenging. And there's this E2LN, which is like you train an ensemble of neural networks, and after just a few epochs, like 10 epochs, you can use the average losses over the ensemble, the average losses of your samples. And if the losses at the beginning are huge, that's a good indication that that's a challenging sample. And oops, there should be an inequality sign there. Ah, okay. Don't play with animations before your talk. So here I want to note that throughout the active learning process, so the whole point is that you're trying to pick challenging samples. And of course, it will result in a very weird thing. So your training sample will be much more challenging than your test sample. So basically, your training domain will be completely different to your test domain. Your test domain should be like come from the original domain. So your test data should come from the original domain, and it should really be just a random sample of your data. Whereas your training set is not that. So so for example, active learning, if you don't pay attention to it, can introduce some class imbalance. So you can choose, like, you can favor one class over another, and then obviously your estimator will think that there's a bias, and it will learn some kind of bias. So you need to kind of either adjust your active learning process, or you need to take class imbalance into account during your trainings, so, like reweight your like apply some weighting in boosted trees, or do some kind of advanced samplings in deep learning or something like that. And as you can see, this is one key result from a paper where they did active learning for computer vision at the ImageNet scale. So it's a pretty huge test, and the random sampler is right in the middle. And the horizontal axis is basically like, this is time, so your annotation budget, and the vertical axis is your accuracy. And of course, like, why do we do active learning? We want to shoot up at the beginning, and we want to be much better than random sampling. But it's important to like notice that like some active learning approaches can even be worse than random sampling. So you have to be very cautious. And like, it depends on the domain, but sometimes random sampling is a very hard and robust baseline, and it's very hard to outperform. I want to mention another result from. There's no citation here, so it's from this paper, this Beyond Neural Scaling Laws paper. So they did an experiment with data pruning, and it was a toy learning exercise, so it was just perceptron learning. But they found that depending on the size of your data and the number of your model parameters, data pruning might make your life worse. So might even ruin things. So basically, if your model is weak, if your model is not strong enough, then difficult samples can easily overwhelm it, and then you're much better off just sending in points that are like a bit further away from decision boundaries. Whereas if your model is beefy and it's strong, it's completely fine. But this whole thing depends on your model as well. And sometimes you implement an active learning process and it's just worse than random, and you show it to your boss and it's of course not a good feeling, but then you increase the capacity of your model and suddenly you outperform random. And now I'm going to show you a very simple implementation of these concepts. I hope the font size is big enough. I'll increase it slightly. Okay, so I use the 20 news groups data, which is it's a text data set where you have these posts or news that are basically it's like an email body, and your target columns are topics of these posts. Like, for example, there's this like atheism, or there are technical topics like hardware and science and religion and politics and etc. And I did some very, very basic data cleaning, and this is what your data looks like. So you have these posts here, these texts, you have a target, like a target class index, you have training and test samples, and you have the target name. And then this is what a post looks like from the autos topic. So it's like, enlighten me on this car, and doors were really small. So this is what your estimator needs to pick up on in order to learn this mapping. And these are the sample counts. And for simplicity, I chose 4 output classes, like two pairs of overlapping topics, like Christianity and atheism, and like some PC hardware and some electronics. And I filtered down the data, and I remapped the target column indices. And then this is our sample count. Of course, it's not humongous, but this is just a simple implementation. And then I use the TF-IDF vectorizer to featureize my sample. Of course, you should really do this in production. I think now, especially on natural language, like the transformers are just much better, and fine-tuning is really works really well. But educationally, it's slightly better because this will return sparse representations. And I can show you a few things. So, this is what it looks like. So, if you use this TF-IDF vectorizer, you get these compressed spatial representations of your features. And then, of course, at the very beginning of every active learning process, usually you don't have annotated data points at all. So you need to do something, basically you need to do data pruning without your target column. And I just used a very, just one very simple idea. So I did an initial k-means clustering on my data. So I wanted to select 300 data points as my initial batch that I sent to the annotators. And I did a k-means for with 500 centroids. And I casually ignored the warning. And then, so normally you just, you would we have 500 clusters. There's no -1 here, so there's like it assigns everything into one of these clusters. And usually you would want to pick the samples that are closest to their centroids, but I didn't do that. I just chose the like one sample from each cluster, and then I basically marked the chosen points. Like I created a column called active learning state, and the chosen samples were called marked, and the rest are called pool. And in order to just keep an eye on the class imbalance, I wrote this check balance function, and currently this is what it looks like. So we see that the active learning process, or so this data pruning process, slightly neglected this atheism class, which is like, yeah, it's just slightly unfortunate, but yeah, it's not a biggie. You need to keep an eye on this. And then some helper functions to get the indices of the fixed and marked points, and the rest of the data from the unannotated pool, and some very. So basically, then I trained a very basic, like just a random forest classifier with some hyperparameter optimization. This is all very basic. One important fact that I want to mention here is that as you go through your active learning service like active learning steps, the number of your data points increases, and sometimes you need stronger models at later stages of your active learning. So it's always a good idea to do hyperparameter optimization, and then in later stages, of course, you will get a stronger model. And then, yeah, we evaluate our model. So we evaluate our model on the training points, which is like the fixed plus the marked points. We evaluate it, we can cheat, basically we can evaluate it on the pool, and we evaluate it on the test data. And yeah, we have a horrendous accuracy first, or test accuracy. And then, okay, now that we have a model, we can implement an active learning pipeline. So we can just fix the points that were marked, and then yeah, these are not marked anymore but fixed. And then we can implement a couple of tools to define the active learning process. So for example, we can compute the uncertainties, and there was this Shannon entropy and the least confident and the margin method, and we can so basically here the input is a probability mass vector that your model returns, and you return an uncertainty or informativeness measure as a floating point number, and we can visualize these triangular simplexes. It's the actual parameterization of simplexes is slightly different. It's called this barometric, but yeah, the mapping I chose is slightly different. But you can check your and I was lazy. I only visualized 1/2 of the simplexes because it's symmetric. And then you can compute the uncertainties of your unannotated data. You can visualize an uncertainty histogram, and of course, yeah, and this is normalized. Oh no, this is not normalized. Regardless, your model is like a bit uncertain at this point, and then we can define isolations and divergences. So let's say that we want to base our isolation and divergence on the 4 nearest neighbors of the points. And then there's a very tricky thing here. So there's this very cool tool with which you can multiply sparse matrices, and it goes even further. So here I wanted to compute a cosine similarity matrix between for isolation between the pool and the pool, and this function computes the sparse result matrix, so it multiplies two matrices for you, in a way that you can set this n-top input argument. And in the result matrix, it will only include the four biggest entries, and this is like a way to do nearest neighbor search. And then basically, then yeah, from the similarities you can compute distances, and similarly you can compute diversities between the pool and your training, or the fixed and the marked set, and then you can visualize an isolation histogram and the diversity histogram, and then you can write a scoring function that will like map your or compute an active learning score from your isolation, your diversity, and uncertainty. And of course, this is way too simple, so you shouldn't do this in production. Even if you decide to linearly combine multiple things, you should at least scale them and have some multiplication factors. And some people like to, instead of linearly combining things, they like to compute products and apply exponents. So this is a bit too simple this way. But yeah, just for educational purposes. And then if you can compute the active learning score, then we can implement this greedy search where we select 1 point for annotation, like one by one, in order to assemble a full batch. And yeah, you can basically select one sample by computing your isolations, your diversities, and your uncertainties, and computing your active learning score, and then sorting by your active learning score and just getting the first point. And then, yeah, you return the index of the first point. And to select a whole batch, you basically, yeah, you have a certain batch size. Let's say you want to select 100 points, and then, yeah, you call this function 100 times, and you mark these points as marked. And then before actually doing this, our class imbalance looks like this. But yeah, when we combine everything together to an active learning service, or like an active learning, a top-down active learning implementation, we will monitor this. But yeah, the active learning implementation goes as follows. So let's say you have a certain number of active learning steps. Of course, this can be event-driven. So usually what stops active learning is that your annotators start telling you that the samples are completely too hard, or something changes. The samples will be so hard or repetitive, or something will happen that they will tell you that now it doesn't make much sense to continue. And then usually you have multiple projects on the side, and you can assign them on something else. So it's a really good feedback. But yeah, so let's say you have 5 active learning steps, and then the steps of active learning is first you select a batch, and you retrain your model, and then you fix the marked points, and we check the class imbalance, and we register our evaluation metrics, and yeah, we repeat this. And then initially you start out, yeah, you get a bit more fixed points, and then your your test accuracy goes up a bit, and you have 100 more training samples and 100 fewer samples in the pool, and then your accuracy goes even higher, and you lose some samples from the pool, and your training samples increase, and yeah, and then another gain in the test set, and etc. And yeah, eventually you end up with some accuracy. This is not the best active learning implementation. This is just to show the main concepts. And this is what I wanted to show you today, and I would like to thank you for your attention and ask you whether you have any questions.
First of all, can I say what a very interesting presentation.
Thank you very much.
For that. I've got 2 questions. Sorry about that. The first one is, could you just elaborate a little bit more on the way you were using k-means to do clustering? You had like 300 clusters. I was slightly confused, and it's just me maybe. I wanted to understand the original problem had 4 classes, yeah, and then you're sort of then clustering, you know, the sample, I guess a trained data set into 300 clusters. What is the essence of that? And I know you also define something called a pool, as well as the other 4 classes. So I want to know essentially how does that all interrelate. And my second question, sorry about this, is a more general one. You mentioned earlier during the presentation that one thing that we tend to do is once we've sort of featurized data sets, you know, we encode it, you know, into some sort of higher dimensional, higher dimensional space. We then have to somehow reduce the dimensions into something that we can visualize, probably 2D or 3D. I was wondering, one of the things that I see with this approach is the cost incurred in doing the nearest neighbor. Is there any benefit in actually doing the nearest neighbor isolation or diversity on the low-dimensional feature space? 2 questions. Thank you.
So the answer to the first question is, so initially you start out from so you have a huge pool of data and you don't have any target counts at all. And since you don't have any annotations, you don't have a model yet. And then you cannot really start active learning yet, because for active learning you need your model. So you need to do some kind of initial data pruning. And usually people just, I don't know, they just choose a couple thousand or 100 random samples, but you can try to be smart about it, and let's say that your and then your just forget the green circles. Now let's say that this is what your feature space looks like before everything. Like you don't have any annotations. And then first in order to just kickstart the whole thing, we wanted to find 300 samples that we can start with. And in order to find these 300 samples that will be representative and diverse, we did the k-means with 500 centroids. And then we selected the 300 biggest clusters from these 500 clusters, and we used samples from those clusters. And the second question, just one keyword.
So the second question was there any benefit in actually, you know, transforming the high-dimensional feature space into low-dimensional by any one of the, you know, dimension reduction techniques, and then doing the actual, you know, the nearest neighbor isolation or the density computation?
So compute. Nearest neighbor is quicker, but unfortunately these isom, for me, isomap was the fastest out of this, but it had some serious distortions occasionally. So unfortunately, I think this mapping is just too costly. After this, of course, nearest neighbor would be much better. But I only used this for debugging, and I tried what you said once, but I wasn't really convinced with the results. And still you need to you need a similarity matrix as the input of this.
Thank you.
Thank you.
Good presentation.
Hi, that's really
Hey.
Thanks again for a really interesting talk. I was wondering if you could give any tips on how to sort of identify practical problem areas where this is a really useful technique to have. Or if you can share any examples where, you know, real world examples where you've sort of really broken the back of something like this by applying.
So, unfortunately, I can't talk about how we apply this. yeah, I cannot give away any intellectual property. But yeah, this is for sure not the complete picture. So, for example, one problematic thing is that usually, let's say that during your feature engineering, usually your feature engineering relies on a set of points instead of just one point. So basically, for example, if you're trying to featureize a user, then usually if you want to featureize the user's activity, you need to compute things from a time window. So when users and time enter to the picture, your selection unit, it becomes a bit blurry. Then you might need to your selection unit, just from one sample, it becomes a set of samples, and then you basically need to put a layer of aggregation on a lot of concepts here. And yeah, when your selection unit is a whole cluster, then again you need to do some active learning in active learning and say that, okay, so if I need to forward the whole user to the annotators, then surely there will be a lot of easy samples from that from that user, and then I will need to make a decision whether I forward all of these points or just like a small sample, just the most challenging ones. And there can be some additional complexity. For example, if you apply this on, for example, named entity recognition, then the output of your model is you have a, let's say, a sentence, and you tokenize this sentence, and for each token you compute a separate probability distribution, and then choosing the selection between sets of probability distributions which are not even we don't share the same size. That's a bit tricky. There might be one sentence that includes a lot of straightforward words and just one very hard named entity that is kind of in between two classes, and yeah, then it's tricky. So there are a lot of things to look out for.
Yeah, a bit related to what you were just talking about. In practice, you might have, in addition to sort of the need for maximizing your informativeness in active learning, you might also have observed some kind of quirks of your data that you want to account for. So like your data got stale in certain kind of aspects, and you notice some changes. So how would you combine that with the active learning approach and the kind of metrics you've chosen? Is there sort of pre-processing, filtering steps, or is there a smarter way to combine?
So yeah, for example, class imbalance is one of these things. So you can either do some kind of filtering, or you can try to prepare your scorer to or adapt your scorer to pick up on these things, or well, maybe not your sample-wise scorer, but then the way you aggregate individual scores needs to some kind of manifest these ideas. So yeah, I would start there.
Hi, what are your thoughts on density estimation methods for selecting interesting samples? So you talked about k-means, but I think there is a whole bunch of literature around estimating density. The second question is, can you hint us to a paper where the approach for isolation and diversity is described?
Yes. I think I have a citation somewhere, and I uploaded the talk to a Google Drive that I think you can access it, but I will add the link to my talk description as well. And about the kernel density estimation, yes. So the answer is that I'm just not as good at them, and yeah, like there are a lot of promising algorithms like the KD tree, and there's a plethora of algorithms, and they are really, yeah, really promising, and I personally want to read up on these. Like the tricky part is that isolation and like once you mark a data point, then it jumps from one graph to the other. So in like if you estimate your kernel density somehow, that representation needs to be, you need to be able to adjust that representation, which like most probably you can do. But yeah, it's tricky that usually like it's high. There's a high dimensionality, so yeah, but definitely very promising. Thank you.
Hi, I hope this isn't too much off topic, but combining active learning with like if your samples start changing over time, so especially if you're monitoring news and some new topics could come up and then like how you're evaluating how you might.
Yeah, I think active learning is almost like reinforcement learning. And in my mind, active learning, so in active learning, you don't assume that your domain changes. You assume that your model is going to become stronger, but yeah, it's not like, if you train a chess player, then as he or she becomes stronger, they will face like other positions, and yeah, these ideas need probably then you will need to discard a couple of so you annotate data points, and then probably you will need to discard a few of them, or because like maybe so over time, of course, your domain changes, and maybe you will need to either discard your old data points or somehow apply some different weights, or make it very explicit in your model, like make your model aware of time. Yeah, this is tricky.
That's it. Apologies if this is already covered in the previous question. You said about the talk slides. I was particularly interested in the notebook that you showed.
Oh, yeah.
Possibly available on the.
Yes, I will share.
Excellent. I was very difficult to look at code, but I can't code it. Excuse me.
Thank you. Yes. I see no hands. I guess. Thank you very much, Dan, for your attention.
Thank you, Mate. And I think if you have any more questions, Mate is around for the rest of the conference, so you can catch him up. We have an hour lunch break now, and after that there will be more talks. And with that, let's thank Mate again.